So, in the last lecture I had given you a physical understanding of the meaning of convection and diffusion. Okay. The convective flux, as we had discussed in the last time, of a quantity is just equal to the velocity perpendicular to the surface times the density of that quantity. Okay. So, the normal velocity times the density is a convective flux, where density is the quantity per unit volume. So, flux of mass is the normal velocity times the mass density, flux of momentum is the momentum density times the normal velocity, and the flux of energy is the energy density times the normal velocity. That is the convective flux which transports in the direction of flow. Okay. The diffusive flux can be in general defined the flux of a quantity on the left side, that is the transport of the quantity per unit area per unit time, is equal to the diffusion coefficient. Okay. The diffusion coefficient has dimensions of length square per time. Okay. I had shown you that in the last lecture. Diffusion coefficient has dimensions of length square per time minus of the diffusion coefficient times the difference in the density of that quantity divided by a thickness. Difference in density of the quantity, that is the difference in the quantity per unit volume, okay, between two locations, divided by the thickness. And negative sign because the diffusion takes place from regions where the density is higher to regions where the density is lower. So, mass diffusion from higher mass density regions to lower mass density regions, heat diffusion from higher energy density region to lower energy density region. Okay. And in this, the diffusion coefficient expressed in this manner, the diffusion coefficients, all of them have the same dimension, length square per time. Mass diffusion, Fick's law, the flux is equal to minus of the diffusion coefficient times the difference in concentration by delta z, and the diffusion coefficient is just the usual mass diffusion coefficient. Fourier's law of heat conduction, Qz is equal to minus k delta T by delta z, or it can be expressed in terms of the energy density as minus alpha delta E by delta z, where alpha is equal to k by rho Cp. Okay. And momentum diffusivity, Newton's law, tau xz is equal to mu delta Vx by delta z. Tau xz, as I said, is actually the negative of the momentum flux in the z direction. I will explain that later in the course, why there is it is the negative of a flux, and therefore, there is no negative sign on the right side in Newton's law. Flux of momentum, if when expressed in terms of the difference in the momentum density divided by distance, the diffusion coefficient is what is called the kinematic viscosity or momentum diffusivity. Or the momentum diffusivity. This is equal to the viscosity divided by the density, and it also has dimensions of length square per time. Okay. So, these were the different diffusion coefficients. Okay. So, diffusion coefficient has dimensions of length square per time, and the convective transport is proportional to the normal velocity to the surface, which has dimensions of length per unit time. So, all these relations apply locally at each point in the flow, but they do not apply on average over the entire domain. Okay. When you average the flux over the entire domain, these relations do not apply, but yet the dependence of the fluxes can be used to formulate dimensionless groups. And in those dimensionless groups, you will have a characteristic length and a characteristic velocity. Okay. And we were discussing for different kinds of configurations, what are these characteristic length and characteristic velocity. So, first thing, if I have a flow within a conduit, okay, if I have a flow within a conduit, okay, let us say I have some flow within this, okay, how would we define the characteristic length and the characteristic velocity for this conduit. Okay. For these kinds of conduits, Of course, if the it is cylindrical, then there is only one length, that is the diameter. Okay. There is only one length corresponding to the cross section, which is the diameter. Okay. But in general, you could have cross sections that are not circular, and in that case, how do we define these? Okay. So, if we take the cross section of a conduit, okay, there is a cross sectional area ACS, okay, of the conduit, okay, and there is also what is called a wetted perimeter. Okay. LW, cross sectional area is ACS and wetted perimeter is LW. Okay. So, for flow within a conduit, the hydraulic radius is defined as RH is equal to ACS by LW, and the equivalent diameter is equal to 4 times the hydraulic radius. Okay. Okay, that is the way it is defined. Okay. And it is the equivalent diameter that is used as the characteristic length in this case. Okay. So, for example, if you consider this for a cylindrical pipe, the cross sectional area is pi d square by 4. Okay. And the wetted perimeter is the circumference of the circle, okay, of diameter d. This is equal to pi d, okay, which gives me d by 4, which means that the equivalent diameter is d itself. Okay. Note that the equivalent diameter is 4 times the hydraulic radius. Okay. So, that is how you define the characteristic dimension for a flow within a conduit. Okay. The average flux, okay, is defined as total transfer rate okay, divided by the total area, okay, total surface area, okay, total surface area of this pipe. The surface area is equal to the perimeter times the length. Okay. So, if this pipe had a length L, the total area is equal to the total length L times the perimeter. Okay. So, that is the average flux, okay, the total transfer rate, transport rate per unit time divided by an area, which is the surface area, the length of this pipe times the perimeter. Okay. So, that is how we define the average flux. Okay. So, therefore, Q average or J average or the shear stress average, okay, would be defined as the total transfer rate of heat, mass, momentum. Total momentum transfer rate is just the total force, okay, the total force that is applied divided by the total area, which is L times the perimeter. Okay. So, that is how you define the transport rates for heat, mass and momentum for flow within a conduit. Okay. And the characteristic length is the equivalent diameter, which is 4 times the hydraulic radius. Okay. Now, how about for flow around a particle? So, you consider a particle which has some volume V and surface area S. Okay. Consider a particle which has some volume V and surface area S. Okay. For this particle, it could be of some irregular shape as well. Okay. It could be of any irregular shape. The hydraulic radius is defined as V divided by S. Okay. Volume has dimensions of length cubed, surface area has dimensions of length square. The ratio of those two is just a length scale, which is a hydraulic radius. Okay. And the equivalent diameter is equal to 6 times the hydraulic radius in this case. Okay. Why 6? Because if I take a sphere, for example, the volume is pi d cubed by 6. Okay. Pi d cubed by 6 is the volume of the sphere. You may be more familiar with this as 4 by 3 pi r square. If you just substitute r is equal to d by 2, you will get pi d cubed by 6 as the volume. The surface area is pi d square, okay, or 4 pi r square, where r is the radius. Okay. So, this is equal to d by 6. Therefore, the equivalent diameter is the same as the diameter for a spherical particle. Okay. So, that is why it is chosen in that way. Okay. The average flux Q average or average flux of mass, okay, is defined as total transfer rate per unit area, okay, divided by S, the surface area, okay, divided by the surface area S. Okay. So, using this characteristic dimension and the characteristic average flux, okay, the dimensionless groups for mass and heat transfer are defined, the Sherwood number and the Nusselt number. Okay. The Sherwood number is equal to the average mass flux divided by a term which has the same dimension as the right side of Fick's law of diffusion. If you recall, the Fick's law of diffusion on the right side is minus d delta c by delta z. Okay. Therefore, this will be d delta c by the characteristic dimension, that is the equivalent diameter. Okay. Okay, so, that is the definition of the Sherwood number. Equivalent diameter is suitably chosen for either mass for either the flow within a conduit or the flow around an object, and Nusselt number is defined as Q average, average heat flux divided by a term that has the same dimension as the right side of Fourier's law of heat conduction, K delta T by the equivalent diameter. Okay. So, these are the definition of the dimensionless groups, whether it is for flow within an object, within a conduit or around an object. Okay. And the ratio of convection and diffusion, okay, the ratio of convection and diffusion in this case is the Peclet number. Okay. Peclet number is the ratio of convection and diffusion. So, it contains an characteristic average velocity. Okay. It contains a characteristic velocity times a characteristic distance divided by the diffusivity, diffusion coefficient. Okay. This is the Peclet number for mass transfer. For heat transfer, the Peclet number is just equal to the characteristic velocity into equivalent diameter by the thermal diffusion coefficient. Recall that the thermal diffusion coefficient we had defined as K by rho Cp. Okay. So, this becomes rho Cp Vc times the characteristic diameter divided by alpha. Okay. What is the characteristic velocity? Okay. For the flow through a conduit, okay, the characteristic velocity is just equal to the average velocity, okay, which is equal to the total flow rate divided by the area of cross section. Okay. This is the total flow rate divided by the area of cross section. Okay. So, that is the characteristic velocity for flow in a conduit. The total flow rate, volume per unit time divided by the area of cross section. Okay. So, that is what is used as the characteristic velocity. Flow around a particle, okay, the characteristic velocity is what is called the free stream velocity. Okay. So, if I have an object moving with respect to the fluid, okay, of course, the fluid close to the object will an isolated object will move because of the object moving. If you go sufficiently far away, there will be no fluid velocity if the fluid is stationary. The difference between the velocity of the object and the velocity far from the object in the fluid is what is called the free stream velocity. Okay. The difference between the velocity of the object and the velocity far from the object. Okay. This is equal to the characteristic velocity in this case. Okay. So, in the case of flow through a conduit, it is the velocity, average velocity of the flow. In the case of a suspended particle, it is equal to the free stream velocity, the velocity far from the object, the difference between the velocity of the object and the velocity far from the object. Okay. So, that is the characteristic velocity, and that characteristic velocity is used in the definition of the Becquerel number. Okay. Similarly, the Reynolds number. Okay. Recall that I had written this as rho v d by mu. Okay. I have substituted the characteristic velocity and the equivalent diameter in this case. Okay. You know very well that mu by rho is the momentum diffusion coefficient or the kinematic viscosity. So, this is V c times d E by nu. Okay. So, this is also the ratio of convection and diffusion. Okay. This is also the ratio of convection diffusion. The Reynolds number, characteristic velocity times the equivalent diameter divided by the kinematic viscosity, which is the diffusivity. So, all diffusivities have the form velocity times a length divided by a diffusion coefficient. Okay. So, that is as far as the definitions of the dimensionless flux, ratio of convection and diffusion is concerned. Okay. So, the dimensionless flux for mass transfer is the Sherwood number, for heat transfer is the Nusselt number. Okay. What about for momentum transfer? If I were to scale the momentum transfer by the diffusive scales, then I would just get the ratio of the wall shear stress divided by into the length scale divided by the diffusivity. Okay, I will just get the wall shear stress divided by the a term that has the same sign as the right side of the Newton's law of viscosity, okay, in an analogous way to the Sherwood number and Nusselt number. Okay. However, the dimensionless flux for momentum transfer conventionally is defined slightly differently. Okay. Recall that when we had done the flow, the settling of a sphere, I told you that the momentum flux, when we had done the flow through a pipe, I told you that the wall shear stress is scaled by what is called the kinetic energy density, because an energy density and a stress have the same dimension. Okay. So, for flow through a conduit, right, the friction factor is defined as the average wall shear stress by the kinetic energy density. Okay. Kinetic energy is half mv square, kinetic energy density is half rho v square, okay, mass per unit volume. Okay. So, this is the definition of the friction factor. Okay. This is what is called the friction factor for flow through a conduit. The shear stress exerted at the wall divided by a kinetic energy density. Okay. I should note that this is what is called the fanning friction factor. Okay. And one has to be careful because in different notations there are the definitions of friction factors differ. Okay. So, this particular friction factor which I am writing here is what is called the fanning friction factor. We know that for the pipe we had done a momentum conservation or a force balance previously. Okay. We can do the same thing for an irregular object. Okay. For an irregular object, okay, with perimeter wetted perimeter LW, length L, okay, and average shear stress tau average, okay, and the pressure difference delta P across. Okay. From momentum balance, the pressure difference across the pipe, okay, the total force that is exerted on the fluid within the pipe due to the pressure difference across the pipe, okay, is going to be equal to delta P times the cross sectional area. Okay. Delta P times the cross sectional area. The pressure times the cross sectional area at the inlet is acting in this direction. Okay. The pressure times the cross sectional area at the inlet is acting in the downstream direction. Pressure times the cross sectional area at the outlet is acting in the opposite direction, because the pressure always acts perpendicular to the surface. Okay. So, therefore, the total force exerted is going to be the difference in pressure times the cross sectional area, okay, and that cross sectional area, as you recall, I had written as ACS. Okay. So, delta P times ACS is the pressure times the area of cross section, which is the force exerted on the fluid due to the pressure difference between the inlet and the outlet. That has to be balanced by the shear stress that is exerted by the wall. Okay. Okay. That shear stress that is exerted by the wall is equal to minus tau W, because that shear stress is acting in the upstream direction. It is tending to slow down the fluid. Okay. That shear stress is acting in the upstream direction on the walls, on the fluid due to the walls. The wall exerts a force in the minus, in the negative flow direction, that is in the upstream direction. The fluid, as it is flowing, is exerting a force in the downstream direction on the wall. The wall is exerting an opposite force in the upstream direction. Therefore, this is equal to minus tau W into the surface area, which is the wetted parameter times L. Therefore, minus delta P by L is equal to tau W into L wetted parameter by A cross section. Note that the cross sectional area divided by the wetted parameter, we had earlier seen that ACS, by LW is equal to RH. It is the equivalent diameter by 4. Okay. So, ACS by LW is equivalent diameter by 4. Therefore, LW by ACS is equal to tau W into 4 by the equivalent diameter. Okay. Because ACS by LW is 1/4 of the equivalent diameter, which implies that tau W is equal to minus delta P by L into dE by 4. Therefore, the fanning friction factor F can be written as minus delta P by L into minus delta P, because delta P is the difference between the outlet and the inlet. Okay. Difference between the outlet and the inlet has to be negative. The pressure at the inlet has to be greater than that at the outlet for fluid to flow downstream. That means that the outlet pressure has to be lower than the inlet pressure. That means that delta P, P outlet minus P inlet, has to be negative. So, minus delta P is actually a positive quantity in this case, because delta P is defined as the difference between the outlet and the inlet. So, delta P is negative and minus delta P is positive. Okay, into dE by 4 into 1/2 rho V average square. Okay. So, this I can also write this as minus delta P by L into dE by 2 rho V average square. Okay. Note that I have written this as the fanning friction factor. Okay. So, I will write this as FF. Okay. There is an alternative definition called the Darcy friction factor, which is defined as just 4 times the fanning friction factor. Okay. So, this is equal to 4 times the fanning friction factor. Okay, just to make you aware that in this course we will be dealing exclusively with the fanning friction factor and not with the Darcy friction factor. In the fanning friction factor, the wall shear stress is non-dimensionalized by the kinetic energy density. Okay. So, in this course we will be dealing exclusively with the fanning friction factor. Okay. Dimensionless flux for flow around an object. Okay. For flow around an object, okay. If an object is moving with some velocity, okay, then the momentum flux is defined based upon, okay, the projected area of cross section. Okay. Note that for the momentum flux, okay, the non-dimensional momentum flux, we have to define, in this case it is called the drag coefficient. Okay. It has to be some average, okay, some average pressure difference, okay, pressure difference by half rho. In this case, I told you that the characteristic velocity is the free stream velocity. So, half rho V free stream the whole square, and this average pressure difference is defined as the drag force divided by the cross sectional area, okay, cross sectional area of the object. Okay. So, this is defined by the drag force divided by the projected area, that is the area that is projected by the object in the direction perpendicular to the velocity, okay, divided by half rho Vfs square. Okay. So, this is physically understandable in cases where the contribution to the drag force is primarily due to the pressure difference between the upstream and the downstream sides. Okay. In which case this drag force divided by projected area is the average pressure difference between the upstream and the downstream sides, and that is scaled by the free stream by the kinetic energy per unit volume based upon the free stream velocity, that is the relative velocity between the particle and the fluid far from the particle. Okay. So, that is the free stream velocity. So, this is how the drag coefficient is defined for flow around an object for cases where the motion of this object causes a substantial deformation of the fluid streamlines around the object. Okay. In the case of slender bodies such as a flat plate, for example, there is virtually no projected area. Okay. The drag force is primarily because of the shear stress exerted on this surface. The drag force is primarily because of the shear stress exerted on this surface. Okay. So, if I had a flat plate like this, for example, okay, and there is flow past the flat plate, the net force, the drag force on this flat plate cannot be divided by the projected area, because the projected area is virtually 0. There is virtually no cross section of the plate that is being exposed to the fluid. So, it has to be divided by what is called the tangential surface area, okay, the surface area of the plate itself, on which the fluid is slowed down due to the presence of the plate. Okay. And in that case, the dimensionless momentum flux is what is called the skin friction coefficient. Okay. This is equal to the drag force divided by the tangential surface area tangential to the flow, okay, divided by half rho V free stream square. Okay. So, the friction factor for flow through conduits, the drag coefficient or the skin friction coefficient. It is called the skin friction coefficient for flow around objects. Drag coefficient if the object blocks the fluid flow and causes fluid to flow around it, and therefore projects a significant surface area perpendicular to the fluid. Skin friction coefficient if there is virtually no projection perpendicular to the fluid. Okay. So, these are the dimensionless groups for momentum transfer. In each of these cases, the dimensionless group is scaled by the inertial scales. Okay. And therefore, this is in contrast or to the dimensionless groups, the dimensionless Sherwood number and the Nusselt number, the dimensionless fluxes, which are actually scaled by the diffusive scales. Okay. This difference is only because of convention. So, in the limit where convection is not important, dimensionless groups that are scaled by diffusive scales, they will all go to a constant. The drag coefficient, friction factor, skin friction coefficient, these are scaled by inertial scales. So, when inertial forces are no longer important, these will scale as 1 over the Reynolds number. Okay. And at high Reynolds number, when inertial effects are dominant, they will scale in different ways that we will discuss in the next few lectures. Okay. So, these are the dimensionless groups. Okay. So, dimensionless fluxes. Okay. The Nusselt number, Sherwood number, the friction factor, okay, fanning friction factor that we will use in this course, the drag coefficient and the skin friction coefficient. Okay. These are dimensionless fluxes. Okay. And then I have ratio, convection by diffusion. Okay. Ratios of convection and diffusion. Okay. These are the Peckley number, that is Vc dE by d and Vc equivalent diameter by alpha. Okay, these are for mass and heat transfer, and the Reynolds number, which is V characteristic equivalent diameter by nu. Reynolds number rho V d by mu or V d by nu. Each of these are velocity, characteristic velocity times characteristic length divided by diffusion coefficient. Okay. So, these are the ratios of convection and diffusion, and then you can have the ratios of diffusivities. Okay. The Prandtl number, okay, which is the ratio of momentum and thermal diffusion. Okay. Ratio of momentum and thermal diffusion is the Prandtl number. Momentum diffusion is mu by rho, thermal diffusion is k by rho Cp. Okay. So, you get the usual definition of Prandtl number, which is equal to Cp mu by k. Okay. The Schmidt number, is equal to nu by d, momentum to mass diffusion. Okay. Okay. Momentum diffusion is equal to mu by rho, and mass diffusion is just the diffusion coefficient itself. Okay. And then there is the Lewis number, which is equal to alpha by d, okay, is equal to k by rho Cpd. So, all of the dimensionless groups that we have seen so far are either dimensionless fluxes, ratios of convection and diffusion, which is characteristic velocity times characteristic dimension or characteristic length divided by diffusion coefficient, or ratios of two different kinds of diffusion, okay, ratio of mass and momentum diffusion, mass and heat diffusion, or momentum and heat diffusion. Okay. So, these are the dimensionless groups that we have used so far. Okay. So, the next class I will discuss about I will review this and discuss about other kinds of dimensionless groups before I proceed to discuss flow through a pipe and flow around a particle. Okay. So, that is the plan for the next few lectures. We will discuss in detail the characteristics of flow through a pipe and flow around a particle in the next few lectures. I will continue this discussion in the next lecture. I will see you then.